right, hello everyone. Welcome to 365. We are making our way through this semester. We are closing in on the end of the third module, which I guess means we're probably, like a third of the way through this semester almost. Crazy how fast that goes. But this assignment is due in 4 days, 11 hours, 58 minutes. Hopefully there's no confusion about when it's due. Let's go ahead and just jump right into it. So hopefully everyone has gotten a chance to make their way through some amount of the challenges, though looking at this, looks like about half the class has done level 1, so maybe that's not so accurate, which is very unfortunate for those of you who have not yet started, because now, you're listening to me talk and you have no context for what the heck this matters for, but that's okay. Who has questions surrounding this module? For things you're getting stuck on, things that consistently just make no sense. Maybe you solved a challenge and you're like, it still doesn't make sense, but somehow I figured it out. Does anyone have any confusion about anything going on in this module that just doesn't make sense? That could use like another primer on it. Not seeing any hands, although we can check the chat. No one said anything there yet. All right, so I'm not seeing anyone with any confusion about some concept here. It all just makes sense. All right, I love to see it. Okay, so in that case, we are going to continue talking about a lot of the concepts here. I believe this is the last day that we're talking about this module, and then we'll move on to the reverse engineering module, which for those of you who love assembly, you're going to love, because guess what? It's more assembly. But after that, we take a long break from assembly. So if you're hating assembly, the end of assembly is somewhat near. Okay, so in this module, though, we are building a web server. Specifically, we're really focusing on a whole bunch of system calls we have to make. Of course, a program, I feel like I've been hammering some sort of concept that all that matters in a program is the system calls that you make. That's not totally accurate, right? There's algorithms also. You have parsing logic. You have some sort of computation you're performing in order to help you make the next system call. We've also been talking about forks. So this idea of processes being able to create a new process. And the way that we show that is through the fork system call. I'm going to say there's other ways to do it. Technically, there's a system call called clone, which you can implement fork through clone. It is very similar, it just gives you way more options. But fork is simpler, and fork is what we're doing in this module, and fork works great. We just have to wrap our heads around the concept of a process forking. So as some motivation for why we might want to fork a process, I think one of the simplest examples of it, I would say, is the ability to run some other program. So for example, if I create a new terminal, echo or ps1 equals $space to make this so that it isn't so long, which is terrible when it's zoomed in. Okay, and we cd live, and what are we in? I think we've been working in shell, which, yeah, good enough. RM core star, we don't care about those core dumps. Those core dumps appear whenever we crash our program, and that is the state of the program at the crash. We have this shell, right? This shell, you're hopefully familiar with the concept of a shell, even if you're uncomfortable with a shell. We type commands into it, it runs some program. When I typed ls, that is the same thing as typing bin ls. There is a file called bin ls, and just like our test program, it is an ELF. Bin ls is an ELF 64-bit LSB shared object, blah, 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 blah. This one has less stuff attached to it. It's a little bit simpler, less going on. It doesn't have this interpreter thing. We don't care about that thing. It's just statically linked. We're not getting into those concepts right now, but it's the same exact idea. You could implement ls entirely in assembly in the exact same way that we're implementing this web server entirely in assembly. Probably ls was implemented in C, though I'm almost certain, in fact, that there's implementations of it in Rust and stuff, and it doesn't really matter. All that matters is that ls does the behavior of what ls is supposed to do. For example, if I run ls, it looks like this. If I run ls space -l, it provides some more useful information like permissions and who owns it and how big this file is. I think if I do like ls-lh, it's going to make the sizes of these things like more human readable. So rather than 8,880 bytes, it's 8.7 kilobytes. I don't know, a little bit more easy to read. And the ls program just does what the ls program is supposed to do. Similarly, if I have cat, right? We know the cat program, cat can output a file. We just have a whole bunch of these very common programs that are just baked into just about every file system and perform these tasks, right? Netcat is a program. Even Python is a program. So if I look at bin Python, it's probably a symlink, but yeah, Python 3, which is a symlink to 3.8. Well, guess what? Python is also an ELF, ultimately. Technically, it's an ELF that then goes on to interpret Python code. Your Python code gets interpreted. Doesn't matter. All these things, though, are ultimately ELFs that are just running x86 on your system. That x86 is making system calls. The system calls are how it interacts with you and its environments. Okay. I just ran a whole bunch of commands. It is very nice that when I ran, for example, ls, that I am able to run ls again after. I'm able to run a whole bunch of programs. The only way that this works, at least in the Linux model of processes, is because our shell is forking and then running another program. If instead, this is totally also allowed, this is how we would do what I'm about to describe in bash. By default, we want this forking behavior. If I run exec space ls, this is not going to fork. It's going to run ls, and then our terminal is going to close because guess what? That was the end of that process, and when that process dies, the terminal is done, and we just lost it. So we are very thankful for this ability to fork. ps1 cd live cd shell. Okay, so let's quickly implement that. So let's implement this ability to run a program. In this particular this particular module, we don't necessarily need that system call. The system call for being able to run an ELF file is execve. So you've actually seen it when you do those syscall traces. The very first thing it says is execve. That's how the program gets started up. That's how Linux loads an ELF file into memory, gets all of the memory set up, and basically puts it right at the start of _start, and code just starts executing. This takes 3 arguments: a file name, argv, which you're probably familiar with from the world of C, envp, you're probably kind of sort of barely familiar with from the world of C, and this is how you start up a program. We can just make this be null, and just work on file name, and go from there. So it's going to be pretty simple. If we want to be able to run an arbitrary program, we're going to need to read in some data, assuming this is the behavior we want implemented. So I want to type in a command, and I want that program ran. So if I do a read system call, I want to read from standard in. So read is move rax0 syscall. Now, of course, we need to set up these arguments. So RDI, our first argument, file descriptor, 0, standard in. 0 just means standard in. That's going to be pointed at our terminal for us by default when we're running it in this interactive shell thing. Move RSI, we need some place to read data into. Let's go ahead and give ourselves some space. We'll say command label, and we'll just say space 100. We're giving ourselves 100 bytes worth of space for our command. So this is how we do that. It's just going to be 100 null bytes. So we'll say move RSI offset command, and then move RDX 100, because you know what? We gave ourselves 100 bytes. We're willing to read from the user up to 100 bytes for them to specify some command to run. So let's go ahead and make that. Actually, we don't care about this GDB thing. Let's swap the order of this so that it just does that. Clear, make, test, And you'll see that we didn't get a $ back telling us our shell is done. It's waiting for something. It's waiting for input. So if I say hello, well, we forgot to exit at the end, so we get a segmentation fault. But if we move rex60 syscall and maybe put RDI to 0 to specify we want to exit with the 0 error code, we're not going to crash anymore. Maybe that's kind of nice. We don't really like crashing, so let's do that. We're waiting. We say hello. What the heck happened? Well, nothing happened. We read in some data and then we exited. If instead, for example, we wanted to output that, well, guess what? It's pretty straightforward. We're just going to transition into doing, instead of a read system call, well, after doing that read, we want to do a write. Write is system call number 1. File descriptor we want to write out to is file descriptor 1. That is standard out. What do we want to write? Well, we want to just write whatever the heck we read in. How many bytes do we want to write out? Well, you could say 100 bytes. Really, what we want to write out, though, is however many bytes we read in. So that came in through RAX right here. So let's just go ahead and save off into R11. Hopefully R11 is not getting messed with by syscall. If we wanted to confirm that, this thing that talks about syscall tells us RCX gets messed with. Well, I keep picking R11. R11 does get messed with. Let's do R10. R10. Syscall is just like this weird instruction that modifies a few registers because it likes to modify a few registers. That's just how it's implemented. So we'll take R10 instead. And then instead of 100, since we've saved this now, we'll write out R10 many bytes. So however many bytes we read in, that's how many bytes we'll write out. And if we run this now we've made it so if I type hello, it prints hello back to us. If we strace that, just to like really make this clear, we'll see, oh, I forgot, do we still have a fork at the beginning of this thing? Oh, that's confusing. We're going to get rid of that so that we're not confusing ourselves. And strace./test. We see that we're currently reading. The way that read, when it's blocking, prints with strace, I don't know, I guess it decides to print the first parameter. It does that because when it goes to print the second parameter, it wants to like print to you the string representation of the buffer of what got read in. That's just the default behavior of strace. Believe it or not, strace is just the program. You could write strace in assembly and make some system calls. If you're curious about that, there is a system call called ptrace. This is the system call that allows strace to do most of its work, but that would be a much more difficult task to implement strace. And so if I say hello, we'll see that now it prints out the second argument of read. This is where I typed it in. It says 100. It says we read in 6 bytes. And then it does write, prints out this. And then like you see like it interleaves, it like prints the actual thing. And that, you know, it's a little bit complicated. If we wanted to see this without it printing, we could do dev null, say hello. I guess that is also confusing. We could do echo hello, pipe that to strace./test, take the standard out, get rid of it, and now we only see what the heck strace is saying, which is it read in hello and it wrote out hello. Okay, so that's a quick like building a simple program that just repeats back to you what you said. The next thing we want to do is instead of printing out what we said, that's certainly a program that you could write. Don't know why we want that program. Is the like let's execute whatever the heck the user said program. As I said, this is the execve system call, and all we're going to care about right now is specifying file name. So we want to make system call 59 because 59 is the syscall number for execve. And if we're ever confused about what the heck execve does, what do? We read the man page for execve. And it'll tell you execve executes the program referred to by path name. And it'll tell you all the important information about the execve system call. But we don't really care too much about the specific details. We're just going to hope it does what our intuition says it does, which is it executes this file name path thing, which turns out to be correct. So we'll do move rex59 syscall. We want to set up the first argument. Again, that's in RDI. The more syscalls you make, eventually you'll memorize the order of these syscalls. If you don't, doesn't matter. You can refer to the ordering. Instead of writing it out, I mean, we're still doing offset command, right? Offset command will work just fine for us. And then we're going to move RSI, the second argument, 0, and move RDX, the third argument, 0, because we're just making those null pointers. We could set up like some, oh, there's a question, yeah.
So to get an input from the user, whatever,
yep.
Is it just like you have the dot space or
so this is one way to do it. So this is using like a data section and reserving space for 100. I could get rid of this and it would work just fine technically. And the reason it would work just fine is because a section is at a minimum and it's aligned to hex 1000 bytes. So it's always at least, it's a multiple of 4096 bytes. So technically right here, I implicitly have space 4096. The reason it's nice to say dot space 100 is in case I go on to create a second label, like something cool. And I want to basically make sure that command is right at this location. So this is going to be at like 402000 or whatever. And then this will be at 402000 plus 100. So it's kind of like within that page of memory that I'm giving myself for data, I'm kind of like making sure these labels are at offsets of each other that give myself space. Technically, this isn't like allocating space though. That's just for label purposes, making sure they're that far apart. Good question. Yeah.
So is it going to wait every time you move it?
Is it going to?
Like just wait for it?
Yeah. So right here, this right here is doing a read system call on file descriptor 0. The way that read works is that it just blocks and sits there until there is in fact something to read. So if, as you can see, like when I did this style, where let's see here, this echo hello strace dot slash test, it never really needs to wait because immediately this hello is available to be read. But when I'm going straight from the TTY, my terminal, and like I haven't pre-typed something in, it has to wait for something. Technically, if you read through the man page for read, you can put read into non-blocking mode, but that's the default behavior. And if you put it in non-blocking mode, it'll just return right away and say it read 0 bytes. So if we do this now and we say offset command, we give it no argv, no envp, we just null that out. Let's see what happens. So we run this. Well, we got this whole thing again. We'll get rid of this. We run this. We run test, and I say hello, and nothing happened. Now, we didn't probably expect anything to happen because I'm saying it's like running this. And like, what the heck is hello? There's no hello program. Well, unfortunately for us, I type ls and still nothing happens. Like kind of what I'm expecting is that if I type ls, I'm going to get the output of ls in the same way that when I'm in my shell, I get the output of ls. Now, the simple way to debug this is to always start with strace. Like what the heck is going on with my system calls? Is my execve failing or something like that? So if we run execve test and it says it's waiting for read, I say ls. It read in ls new line. So when I press enter, there's a new line, and that new line gets read in also. So then I did execve ls new line, and it says no such file or directory. So we just tried to run the ls new line program, and that does not exist. So it's kind of like a little bit of a mess here, right? Because I just said if I press new line, or if I hit enter, which is how I send the input, it's going to put a new line in there. So that like doesn't really work for us. There's like ways to get around this. So for example, I can do echo-n, which means don't put a new line, whatever the heck I type to you. And you'll see that it does test, and then it doesn't put a new line before this $sign. Whereas if I did test, it does put a new line. So if I do echo-n test, and then do strace / test, well, I guess we want ls instead of test here, we're going to be able to get it to read ls without a new line, which is pretty cool. However, it still does not work. The reason this does not work is that /ls, as in my current working directory, there is no program named ls. This behavior of like ls automatically converting to bin ls, this is something our shell is doing for us in the background. Now, fortunately, in our shell, we can also just type bin ls, and bin ls typed out fully also works. This is where the ls program is. It's in bin ls. It's not just ls in the current working directory. So if instead I type bin ls and send that without a new line character, let's see what happens. Well, we get a whole bunch of output, and the reason for that is what we're s-tracing now is ls. This is all of the syscalls that the ls program is making. You can see even a simple program like ls is making a lot of system calls. And that's because of the C runtime. The C runtime is like mapping in a whole bunch of libraries. It's setting up the permissions on those libraries correctly. It's setting up the heap. This like brk system call is like setting up the heap, which we haven't even talked about, but maybe you've heard of the heap before in other contexts, right? Like when you type malloc in C, that's the heap. This is setting up the heap. It looks like for some reason it wants to look at proc file systems. What else is it doing? It's doing these IO control things. It's doing open at instead of open. Turns out there's a whole different variety of the open system call called open at. This get dents, this is getting directory entries. I mean, I'm not expecting you to know all these syscalls. As I said, there's like 300 system calls. If we look for get dent, get dent, this is a system call that is like how you get information about a directory. So we don't need to know how that system call works, but that's what's going on there, which makes sense. ls needs to get information about some directory. And then eventually we see this write. So we're familiar with the write system call. Somehow it like parsed this all out and built up this string and then sent this string to file descriptor 1 ultimately. And that's how it works. So we can see, if we do it without strace, we'll see this works. Again, if we do /test, and even if we type bin ls, that doesn't work because it's got that new line character. So probably what we want to do to handle that new line character is, let's see here, we want to convert that new line character into a null byte. There's also like no guarantee when we have this dot space. So technically, this whole data section is just 4,096 null bytes. So it is null byte initialized, but we really want to make sure that we definitely end our input with a null byte. And so like the correct simple implementation, in the same way that in the web server, you're searching for a space character and the second space character and converting that into a null byte, here we're just going to look for the first new line character and convert that into a null byte. So the way that we can do that is we're going to set up a loop. So we'll just call it L1 for loop. We're going to look at RSI. So RSI contains the beginning of the input that we just read in because we very nicely set that up to do this read system call. And we're going to pull 1 byte out of RSI. So we're going to, well, we've got a few options. We could, let's see here. We could pull 1 byte out of RSI. Let's just do that. Move AL. So we're going to move into the 1 byte into the lowest byte of RAX. And what we're going to pull out is RSI, right? So this is pulling the very first byte out of our command because our command is sitting in RSI, this location in memory. We want to look at the first byte of what they just typed in. Our goal is to find the new line character. We are going to compare AL with new line character. We're looking for this new line character. If we find it, so we'll say, I don't know, end 1 will be like when we can leave this loop. If we found it, let's jump to end 1. So jump if equal, to end 1. Otherwise, we want to add RSI 1, so we're incrementing RSI by 1. By the way, I keep doing add RSI 1 to increment something. I should point out that there's also an inc RSI, which is the same thing. So you might see that version instead. I mean, probably makes more sense. Increment, just increment it 1. I don't know, whatever you prefer. And And then we want to jump to L1, right? This simple algorithm is this is the basis of any walk memory algorithm. In this web server, you're going to be writing a walk memory algorithm. It's just instead of looking for a new line character, you're looking for a space. So we're finding this new line character, and at this point in time, and I'm making a lot of assumptions that I'm writing this code correctly. At any point, I could be writing this incorrectly, and I need to look in GDB to confirm some assumptions. So it might be nice to debug your work, but I'm going to assume it's correct, hopefully, and then debug it if it's wrong. So at this point, we jumped out to end 1 because RSI is currently pointing at a new line character. So what do I want to do? I just want to make that be a 0. And specifically, we need to specify here that this is a byte pointer because now this 0 is ambiguous. In this case, there's no ambiguity because AL is a single byte. In this case, what the heck is 0? Is 0 1 byte, or is it 8 bytes, or is it 2 bytes, is it 4 bytes? We're saying it's 1 byte. So replace this new line character with a null byte. This is the algorithm for doing that. You'll notice there's no system calls right here. It's not just about system calls. It's system calls plus like algorithms is what a program is. Here's a nice little simple algorithm that is the find the first new line character and replace it with a null byte algorithm. Has a very fun name to it. And now we should be able to run this, and we should be able to now not need to do this echo-n thing to be able to run bin ls. So let's make this. Let's run /test. Let's run bin ls. And sure enough, now bin ls works. We didn't fix this problem of ls working, though there is a solution to that, actually. So a very simple solution is, I guess, let me start with the correct solution. The correct solution in terms of what your shell actually does is it uses this path environment variable, and it just like looks in all of these directories one by one, separated by a colon. Just that's what it is. That's how it was defined. It searches through all of these directories and says, does that file exist there? Does that file exist there? Does that file exist there? And if it exists there, it uses that as the path. So that's what it actually does. Let's write the simplified version, which is your program will be in /bin or it doesn't exist at all version of this. A lot simpler to write. And the way we can do that is I'm going to actually rename command to be input, right? This is our input buffer. So we'll say read into input. And I'm going to just put .ascii bin that, right? So I didn't put .string. If I put .string, there's a null byte here. And this is a null terminated string, except we don't want a null terminated string. We want to continue on into whatever the heck the input is. So this is kind of like a cheap solution to our problem, is just literally in memory, put /bin/ in front of this input buffer, because this is all just sequential memory. And now we're kind of like getting this string concatenation behavior for free without having to write like starcat or something. We just like, that's how the data is laid out. As long as no one messes with these bytes, we're good to go. And now instead of doing offset input, we'll go back to offset command and we're gonna run that. So we're literally just laying out memory in a way where we get starcat for free. And now if I type ls, make ./test ls, I don't need to type bin ls. Unfortunately, we've still got bugs with this because now it's looking for /bin/bin/ls and that doesn't exist. But I don't know, you can write your program however you want. You're just tacking on more algorithms and more algorithms to get whatever the heck behavior you want to define for your program, according to the specifications of what that program needs. Okay, so we implemented a very simple shell, except one problem, well, a couple of problems. The first one is our shell has this nice little like indicator whenever you're typing a command to say, hey, you're typing a command. Let's go ahead and add that. So we'll just say prefix .string, and instead of $space, we'll use greater than space. And we're just going to output that. It's that simple, right? There's nothing like fancy about this $sign thing. Just someone wrote that to standard out. So the very first thing we're going to do is write that to standard out. Move RAX1, 1 is the number for the right system call. Maybe you're starting to memorize this, that the 1 is the right system call. Totally fine if not. Move RDI1, R1 is standard out file descriptor. Move RSI, this offset prefix thing. Offset prefix. Move RDX, 2 bytes. I want to write 2 bytes. I want to write greater than space. I don't want a new line character because that's not cool. I want my cool shell to have no new line there. And then I want to make a syscall. And now if I make this and run this, look at this sweet shell that I've got. Instead of $space, I got greater than space. And now I can type ls. But now we're thrown back out into our original shell because we don't have a loop. If we want this to just continuously run, what do? We don't exit. We jump back to start, right? Just go back to the beginning. We'll just keep looping forever. We say there's no way to exit this situation. So let's run that. /test, ls, and it didn't work. Why did it not work? The reason it did not work in this whole build-up towards this discussion of fork is because execve consumed our process. We lost this process. As soon as this syscall right here happens, where we do RAX59, the execve system call, as soon as we do this syscall right here, all of our memory just got wiped out, got replaced with the ls program, and there's no, we're not hitting this instruction because it's gone. This program is gone now. It's been replaced with ls. If we want to be able to do this looping behavior, this is where something like fork comes in. I don't want to consume my process. I want you to create a new process. There's a question. Yeah.
Sorry.
No, it's all good.
I'm just a little confused about at the very bottom. How did you get command to become thin with the?
Yeah.
I understand if you did ASCII, but like, how is that also concatenated?
Yeah. So let's actually look at this in GDB. So if I do gdb./test and I start my program, I want to look at, let's look right here after we read some input. So we're going to break at this system call here after the second system call. So we're not going to just step instruction by instruction. We're going to go to targeted points and look at memory. So this happens, actually, I don't think I've shown disassess. I've just been doing like x/8i to print 8 instructions. This is going to show me all of start. Let me set disassembly flavor Intel so that it doesn't look like this. In case you're wondering, this is AT&T syntax. It's the default for GDB. You got like all these $ and this, and all the arguments are backwards. It's a whole mess. Some people like that, but I don't. So let's go ahead and break at this second syscall. This second syscall occurs once we've executed this. This is us bringing in data. So we'll break before that happens. So we're going to break right at this system call. We will continue. And so we haven't read data in yet. You'll see we did print out our nice little shell prompt. Let's look currently at the contents of memory. So we've got this prefix, we've got this command, we've got this input. So if I do x/s prefix, oops, that's fun. Cast it. Well, can you do that? Okay, well, we'll just go off these things. So this thing right here, the initial thing was pointed at prefix, right? So the very first thing in memory of our data section, these are just laid out in order, is the prefix. And so when I did that right system call right here, if I look at x/2c to print 2 characters at this address, we'll see that there is a greater than character and then a space character, or decimal 62, decimal 32. You can print this however you like to look at it. If you want to print it as 2 hexadecimal bytes, we can do that. If we want to print it as 3, we'll see there's a new null byte right after this. If we want to print it as 16, this is greater than, this is space, this is null byte, this is slash, so let's actually probably you don't have ASCII memorized. So let's go ahead and do 16 characters. Though this is, I'm going to zoom out a little bit, and no, it's not worth it. Let's do 4 characters. So we've got greater than space null bytes slash, and then let's do 4 more bytes, bin slash, let's do 4 more bytes, null byte, null byte, null byte, null byte. So we can see that this lines up, this is our initialized memory, right? We've got slash space, and then because of string, there's also a null byte here at the end. So greater than space null byte. And then this ASCII thing, because we did .ASCII instead of .string, there's not going to be a null byte at the end. Now, technically, there will be a null byte because of this region, but roll with it for a second. We have slash bin slash following that. So slash bin slash. And then we've got a bunch of null bytes. I'm telling you, and we'll see, this address right here, 402.008, is input. So let's go ahead and look back at our disassembly and see right here, this is our input. So we're reading into 402.008. So the very first byte of that read system call is going to overwrite this null byte right here, which immediately follows slash bin slash. So if we step, it'll become much clearer. If I type ls enter and I look at memory again, so let's print, we'll print 16, well 15. We got greater than space null bytes slash bin slash ls new line. Does that answer your question? Like it's just literally laid out in memory that way. Cool. Yeah, that's it's kind of like it works here. Now, if we did that path thing where we were going to try and search like a whole bunch of different prefixes, this like simple solution wouldn't work. And also we just pointed out that it fails if I type bin ls, because now it's bin ls and that path doesn't exist. But it's a very simple solution to our problem and works by just laying out memory in that precise way. So if I make this and I run this and I type ls, it works. It doesn't continue though, right? Even though we said jump back to start after you do this, like it shouldn't even be possible to hit this exit syscall. I could even remove it if you're worried that's what's happening. And run it again and type ls, it still exits. And it exits, we know that because, well, let's make this even clearer. Let's do this many bytes. So it's like jumps out a little more at the screen. 3, 4, right? Make ./test ls. And then it goes back to our original shell. We've got like a shell within a shell. Our shell is starting our version of a shell. And we don't get to continue, even though we said very explicitly, hey, jump back to start after you do this execve. What the heck? What's going on? As I said, this consumes our process. Our process is no longer after this syscall, assuming execve succeeds. If execve fails, actually, we can see that. This is kind of cool. If I say hello instead of ls, bin hello doesn't work. Guess what? It did jump back. As long as I type something that can't be exec and our execve syscall keeps failing, our shell will keep looping very nicely as we want it to. As soon as I type a real command, well, sorry, it's gone. The reason for that is it's consuming it. So if we want to prevent this consumption, or at least like handle the fact that it's consuming it, this is where fork comes in. So let's do fork, which is syscall 57, move rex 57 syscall. There's no arguments to this guy. At this point, written as it is, we're going to run the ls program twice. Does anyone have any confusion about why we're going to run the ls program twice? We've previously talked in past lectures about the fork system call, and we did like a write after it, and then the write happened twice. In exactly that same way, this execve is going to happen twice. So let's prove that to ourselves. We'll make it, we'll run it, we'll say ls, and guess what? We get the output of ls twice. The reason for that is because it just executes this next instruction in both processes. then executes this instruction in both, and ultimately executes this syscall in both. In both processes, we just continue executing here. The thing you need to do whenever you do a fork system call, unless you literally want this like do the same behavior twice thing, just about always though, when you use the fork system call, the very next thing you're going to do is you're going to compare RAX with 0. And the reason we're going to do that, as we've kind of talked about multiple times, man to fork, return. On success, the PID of the child process is returned in the parent and 0 is returned in the child. RAX is the only thing that will be different in these two processes. It's not completely true, but in terms of memory and registers, that is true. RAX is the only register that got modified as a result of this syscall. That's the only way you can differentiate these two processes. And if you want to differentiate something, guess what? That's the compare. And it's either 0 or it's not 0. That's the distinction we're making here. As we said in the child, it is 0. So if it is 0 in the child, let's make it so that the child runs this, and that the parent goes back to the start. So we'll say jump not equal. So if it's not equal to 0, we're in the parent. Let's go back to the start. Otherwise, we're going to run this. So in one of these processes after the fork, we're going back to the beginning as a result of these two instructions. In the other, we're following through and doing an execve. So always, 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 for all intents and purposes, compare RAX 0 is the very next thing you're going to do when you ever do a fork system call. And you're going to divert control flow in these two things. In this case, I'm doing an execve. You might not do an execve after. You might have one thing, and in the web server's case, going back to that accept system call. But here we're doing a shell, so we're going to do our execve. Now there's something a little bit weird. As soon as you got two processes and these two processes are running at the same time, they are running at the same time. That's what your mental model should be. Technically, if you have one core running all of this, one core can only do one core's worth of work. So they're not running at the same time. They're just rapidly jumping back and forth between which person's running. But for our purposes and any modern computer, you got multiple cores. Probably they're both scheduled simultaneously, let's just say. Keep it simple. They're running at the same time. That means we do not know what's going to happen first. ls could happen first, or print our shell could happen first. These are kind of, in our world, happening simultaneously. I'm going to tell you right now that printing out greater than, just doing the single write system call is like way faster than doing an execve system call. The write system call is so much faster than the execve system call, unless if we were over a network or something. If this was over a network and we had to wait for the network to confirm that it sent our packet out for us, I mean, in that case, this write could be slower than our execve. But in our case, how we've got this set up, the write is way faster. And so I'm pretty sure if we run this 1,000 times, we will always see the greater than printout before ls prints out. Okay, so let's make sure that this works. So let's run /test. We'll type ls, and as I said, greater than space happens, because that write happened first, then ls happens. Now this probably isn't the behavior we want. Probably would be really nice if it prints this and then it did greater than space after that, like if that always happened. So you could I don't know, you could put a loop and you could count 10 million times, 100 million times and make your CPU run really and just sit there and wait. I mean, we'll do that. Let's say move RAX, we'll say 1 billion. We'll make our CPU go in a loop 1 billion times. And if that takes too long, we'll slow it down. But I think 1 billion, well, let's start with 100 million. We'll make our CPU go in a loop 100 million times, and then hopefully that gives ls enough time to do its thing. This is like our simple solution. We'll show the correct solution after. We'll compare RAX with 0. we'll say this is L0 because we have an L1 label, so we'll call this loop 0. Jump not equal to L0. So if it's not 0, go there. Otherwise, sub RAX1, jump L0. Wait, hold on. Something doesn't make sense here. Jump not equal. Oh, we need to do this before our loop. Initialize before the loop. And we'll just do this, right? So we initialize to 1,000,000. We decrement by 1. Compare if it's 0. If it's not 0, go back to the loop. Decrement 1. Compare if it's 0. And we'll just keep looping, right? This is our quick and dirty solution to this timing problem because this write is so much faster. Make test ls. Well, 100 million is pretty quick, unfortunately, unless we made an issue. Let's go to 1 billion. Make /test ls. All right, something's making me nervous. Compare RAX 0. Jump not equal. If it's not equal to 0, shouldn't be equal to 0. Go to loop 0. We'll try it. Okay, hold on. I don't know why my looping thing isn't working, but instead of just like sitting at this and trying to execute it in my head, let's execute it in GDB. Start I, step or set disassembly flavor Intel, X for I, RIP. We'll do display for I so we can always see RIP. Okay, so we're initializing RAX to this value right here, which I think that looks correct, right? How many? Got 3 zeros, we got another 3 zeros. Oh wait, this is 10 million, isn't it? We're off by an order of 1,000, aren't we, in this? Okay, let's write out 1 billion correctly. It turns out it's very hard to write 1 billion. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, hopefully that's 1 billion now. I was trying to say, like, well, how is the CPU doing this so fast? Make it, run it. Okay, so you see how it like had that little pause there? That's a good sign. All right, there's a little pause there. That pause should be long enough for ls to run, no problem. ls, boom, we got our solution. It works, right? We just make our program 1/3 of a second slower, 1/2 a second slower, and you know what? We made it work. It works fine. Now we've got a solution. This isn't really, I mean, hopefully you're not thinking this is like the only way to do this. This is not the only way to do this. There is a wait system call. Wait. What? Oh, it's wait for. This wait system call here, if we look at man to wait, is wait for process to change states. So this system call right here it's got a lot of arguments to it, and some of them are pointers, and maybe you're getting nervous that I gotta like fill in memory in some way. It's not that bad. There is a simple thing. So the first thing we want to look at is like, what is this PID argument, and like, what do we do with it? If I look at PID, the wait system call suspends execution of the calling thread until one of its children terminates. So this is like the description of what we're looking for. We're waiting for ls to terminate before we continue. It says, the wait PID system call suspends execution of the calling thread, blah, 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 specified by the PID argument. So we can wait on a specific child. Alternatively, we can wait for any child. So we don't need to know which child. Though if you think about it, as we said, that fork system call in the parent isn't getting 0 back. It's getting something other than 0 back. That something else is the PID of the child. So we could save that and roll with that. Alternatively, we've only got one child. So we'll just wait for any child, and that is -1. And we could read through this documentation. It'll say somewhere that this W status thing, you can just make that a null pointer. It'll work just fine. You can make this 0. And so we can just do wait PID -1, 0, 0, and that'll just wait until the child is done. So let's do that. The issue is we can't do that up at the start because the very first thing we do can't be waiting for a child. That's not going to work. So instead, we'll jump not equal. Instead of start, we'll say parents. And we'll jump to parents. And right here, so we're kind of like interleaving our logic. We're going to not be very happy in the child. If this execve system call fails, we're going to fall through to the parent's logic, and it'll be a whole mess. So really, we should also like compare RAX with 0 or just exit. If we ever reach right here, we should probably just exit. So move RAX 60 for exit, syscall, move RDI 1. We'll just say exit with error code 1. If execve fails, we don't want to mess around with this. Otherwise, it's going to fall through into parent logic and like the world's a mess. What we want to do now is this wait for system call, so 61. So move RAX 61, move RDI -1. As we said, we can just pass -1 to wait for any of our children. Move RSI 0, move RDX 0, syscall. And then jump back to start. Jump _ start. So this is what the parent does. It waits for the child to finish, and then it goes back to the beginning. Make /test ls who am I ls, right? It works now. And we've got this non-artificial timing thing. In the building a web server module, you do not need to use this wait PID system call. I mean, we showed how easy-ish it is. Of course, that's because I've used this system call before, but you could figure out the information for it reading the man page. At any point in this module, you're making a system call and you're like, how the heck does this system call work? The challenge is telling me you must make the bind system call. Well, first watch the lectures, the like video lecture things that talk about these system calls. And if you're still confused, read the man page. It'll give you a very nice technical description of what that thing does. And if that's still confusing, then ask on the Discord, of course. Okay, so that is our very, very simple shell. You'll notice that ls-al does not work. This is not a valid program path. /bin/ls space -al. That thing is not a valid path that exists. If we wanted to be able to handle this space thing with arguments, well, that's where argv comes in and envp comes in. But in this module, you're not using execve, so we're not going to go into filling that out. But that's what you would do if you cared. You would find the space. I mean, it's kind of similar to the web server. You'd be finding a bunch of spaces and replacing them with null bytes and filling in memory now with a whole bunch of null terminated strings to fill in argv. But we're not going to do that here. Okay, does anyone have any questions about this? I know I went pretty quick through this building a shell thing. The purpose for that is just to remind everyone, right, that we're creating these simple little algorithms in assembly and making a bunch of system calls. And that's all any program is. Instead of writing a web server, we wrote a shell. You're going to be doing the exact same thing, though. Making system calls and writing algorithms. I mean, technically, that's any program. If you want to implement a web browser, guess what? You do the same thing. It's just system calls and algorithms. What else is there? But hopefully, the web server is not too difficult to do. Yeah. Any questions about any of this or any topic related more specifically to the web server? Yeah, there's a question. Yeah. You're saying for execve? Uh-huh. Uh-huh.
they ever be null or how?
So let's see here. In building a web server, so there's a few answers to that question. Let's see here. So for example, in this listen system call, it takes two parameters. It takes a socket file descriptor. That's just going to be the file descriptor you got from socket previously. And then it takes this backlog thing. This backlog thing, I mean, it does something, but as you'll see on the slides, I tell you just like pass 0. So this is a situation where passing 0 works. And the reason we know that passing 0 works for this backlog thing is if I do man to listen and I search for backlog, it says the backlog argument defines the maximum length to which the queue of pending connections for sock FD may grow. So basically, you can imagine you're building this networked web application or this web server, right? And you have 10 connections come in all simultaneously, let's say, and you're only processing them one by one. We're going to ignore this whole like multi-processed thing. If you set backlog to 5, those last 5 connections that come in will just get rejected. It'll return to the client like networking stuff that means you can't connect here. On the other hand, as it says here, and it says that if a connection request arrives when the queue is full, the client may receive an error with an indication of econ refused, or if the underlying protocol, so this comes down to like TCP stuff and like the protocol, which we'll get into in a later module, supports retransmission, the request may be ignored so that a later reattempt at connection succeeds. So the way that it actually works in the world of TCP is that it just gets no response, and then it tries to connect again on the client side. It just automatically knows to retry. Let's see here. Now I'm wondering. I figured this documentation would say something about the behavior of passing 0 to this thing. I am not actually totally sure now for this specific example. There's a chance that by setting it to 0, the documentation isn't saying it, but it puts it to some default maximum queue size. I'm not 100% sure on that. Or there's a chance that when we specify 0, that queue length is 0, and so anyone that connects besides the first person is getting rejected. I'm actually not sure about the behavior. I'll say that in this module, you can pass 0 to backlog because we're not going to make you handle that situation. On the other hand, though, this except system call is probably a better example. So there's kind of like a difference between 0 and null. Null implies it's an address that's 0. In this case, this sock adder thing, this adder, as you'll see here, I also say just pass null. And I'm much more certain that the except system call will say what the heck happens if adder is null. It says the argument adder is a pointer to a sock adder structure. This structure is filled in with the address of the peer socket as known to the communications layer. So I'm telling you to put null here. If you didn't put null here and you gave it a valid address for it to like fill in memory, what it's filling in is basically like the IP address and port of the person who's connecting. So it would tell you the IP address of the client connecting. But the documentation says here, when adder is null, nothing is filled in. And that works for us because we don't care about collecting information about the client connecting in. So, I mean, most web servers do actually like log all these requests coming in with like the IP address. The way they're pulling that in is by making this argument not null. So, I mean, to answer your question, it's not really maybe the most satisfying thing. The answer is like the documentation says what all these arguments do and what happens if you pass, for example, 0 or null to it. If there is like in this case, we'll just do nothing if you pass us null. Does that answer your question? Okay. Any more questions about this? About this module in general, about making syscalls, about walking through memory? So I think we've basically covered everything you need to do for this assignment. Oh, there's a question on Twitch. I forgot to check here. Cool. It sounds like it was answered, but we'll look at it anyways. What? It's been answered? Yeah. Oh, not answered. Wait. Which one of these is not answered? Is it just not appearing on my screen? You're missing messages. Well, that's unfortunate. Do you know what the question is? Oh, it's been answered. All right. I think we're good. Oh, there is this question. What does move R10, Rx do in this context? Okay, so if we look back at this code, move 10, R10, Rx. So I talked about this briefly while we were implementing this. Though there's a chance it's no longer relevant. Oops. Yeah, it's no longer relevant. So for the current state of this program, when we implemented this shell, I could totally get rid of this instruction. It's doing no value to us. It's just making the CPU do work that it doesn't need to do. Originally, though, and the reason you might do something like this, and you will do something like this in this module, right after the syscall, you're going to have an instruction, depending on the system call, that's kind of in the same way that this is all associated with setting up the system call. This instruction is associated with like persisting the results of the system call. REX contains the result value. And in this case, this is a read system call. A read system call tells you how many bytes did I just read in. And if for some reason I need to be able to refer to that number later, but like I'm going to be modifying REX, so like I can't just keep it in REX. If I've never modified REX again, great. Then you can just keep it in REX and refer to REX at a later time. But as we see here, like REX, you're constantly messing with REX. If I want to save this thing off, I put it in a register. If I've run out of registers to save temporary little values to, at that point, put it in memory. I'm going to tell you right now, probably you have enough registers that if you need like a 64-bit value temporarily saved, just start filling in registers. I will say though, I think I've made this mistake multiple times already in this class. I, for some reason in my head, default to using R11 as my temporary register. Don't use R11. Very surprisingly, RCX and R11 is not intuitive. You might say, why the heck does it do this? It does it for good reason, and either way, this is what happens. When you make a system call, R11 and RCX are going to get modified. So if you start saving things that you want to refer back to later in RCX or R11, you're not going to be happy. You're going to be incredibly confused why these values are suddenly changing. I've spent hours debugging issues like this before. In your head, just think to yourselves, I will not use RCX and R11 to save values. They're dangerous because they will get messed with when I make a system call. Okay, otherwise, but you can use, R10, R12, R13, I don't know, is there R14, R15? How many registers are there? I don't know, you just keep counting until the assembler tells you you can't use that. R23 doesn't exist. Cool. All right, passing, n doesn't produce \n. Oh, really? Let's see. ls, and we'll press Control D. That's kind of fun. How does that? Whatever, we're not going to go into that, but cool. It looks like you can type in your terminal and press Control D, and it'll actually send it to the program without a new line character. So that's another solution. At the beginning of class, we're using like echo-n. I guess that is another solution. You'll see I just hit Control D again. I guess maybe it's hard to see that I did that. And it printed the same thing out. That's because bin ls is still just sitting there in memory. I did a read system call. By hitting Control D, I read in 0 bytes. Control D is like this special thing that generally means like end of file, or in this case, it's just like there's nothing left. So I hit Control D, it did a read system call. It stopped blocking because I did Control D, and it did a read size of 0. And then it went on to the fork execve logic, and it's just execveing whatever the heck is sitting in memory. I read in no new bytes. I didn't modify anything. So bin ls is still sitting there, and it execve'd bin ls again. If I hit Control D again, well, it looks like we segmentation fault. At some point, I don't know. We'd have to step through in GDB while hitting Control D a few times. Seg faults it. There's some reason that could be discovered through GDB why it crashes under this behavior. All right, any final questions? Otherwise, we're going to end early. I guess only like 5 minutes or 10 minutes early. Because we've covered all we need to cover. It's great. And then next week, we'll jump into reverse engineering. It's going to be a lot of fun. Instead of writing assembly, you're going to be looking at assembly. Way more exciting. Cool. All right. Thank you all for attending, and good luck.